Okay, so it's being recorded now. So in the second section of chapter 1, we just introduce the initial value problems. The whole chapter of chapter 1 is introduction to differential equations. We just discuss some basic concepts and terminologies. So what is initial value problem? Okay, we talk about differential equations in section 1. If you add some conditions, initial conditions on the differential equation, then we call it initial value problem. Okay. So like when you try to solve an equation of motion for some object, you need to give the initial conditions, the initial position, initial velocity. For example, when you consider the motion of a particle, right? So these conditions are necessary to solve the problem completely. So what's the formal definition of initial value problem? We say on some interval I containing x0, the problem of solving an nth order differential equation subject to n side conditions specified at x0. Okay, so you don't have to worry about those i's. It just means the problem makes sense on some region. But you do need to specify a point inside the region. We call it x0. You give all the conditions initially at that point, okay? In addition to the differential equation. So we're talking about the nth order differential equation. We know what it means by the order of differential equation is the highest the derivatives in the equation. So you can rewrite the equation as the nth derivative of y with respect to x equals a function of all the variables x and y's and the derivatives of y's. Okay, so this is a general differential equation of nth order. So that's the differential equation. The highest derivative is n, okay, as you can see. And in this equation, we only have two variables. X is the independent variable and y is the dependent variable. We are trying to solve for y as function of x from this equation. All right. And all the initial conditions are specified at one point inside interval I, and we call it x0. So the initial value of the function at the x0 is y0, and the derivative of the function at the x0 is y1, and so on. Okay, up to the n-1, the derivative of the function at this point at x0 is y n-1. So all of those y0, y1, up to y n-1, there are numbers given in the problem. Okay. Plus the x0. Okay. So with all those initial conditions, we can solve the problem completely. We can determine, the behavior of the function completely. So this y1, y0, y1 up to y -1 are arbitrary real constants. Okay. Really depends on the problem where the initial values are for those functions. So that's called the nth order initial value problem, and we use IVP for the short notation. So, for example, if we have first order initial value problem, then we only need one initial condition. Okay. So the equation may be like dy over dx equals f of x, y. So this is the first order differential equation. And we only have the initial value of the function at x0, which is y0. So you only need one initial condition for the first order initial value problem. Similarly, we can have a second order initial value problem. But this time you need two initial conditions. Okay, as I said before, if you have a first order differential equation, then you just need to integrate once. In principle, to find the function y. And when you integrate once, you bring up one arbitrary constant that needs to be determined by the initial condition. So we only need one initial condition for first order initial value problems. But for second order differential equations, when you try to solve y from this equation d2y over dx2 equals f of x, y prime, you will need to integrate twice to solve for y from this equation. So when you integrate twice, you're going to bring up two arbitrary constants that will be determined by two initial conditions. That's why you need more conditions for second order initial value problem. Okay, so we just give the initial value of the function at x0, we call it y0, and the derivative of the function at x0, and we call it y1. So those are given numbers. Then you can solve the function y completely without any arbitrary constants. Everything will be fixed. Any questions? So pretty straight, isn't it? Any questions from the online people? Nope. Let's go to the next page. So let's look at some examples. Suppose we have a first order initial value problem. So we want to solve the equation y prime, the first derivative y, plus 2x y squared equal to 0. So that's the differential equation, and we have one initial condition since this first order. Okay, we only need one initial condition. Okay, so the initial condition is y of 0 equals -1. All right. So so we claim the solution to the differential equation is y equal to 1 over x squared plus c. So later we're going to discuss how we can solve this differential equation, but right now let's just accept this result. And you can easily check that's indeed the solution of the differential equation by plugging this function y into the differential equation, and you will see the equation holds. So we need to find the derivative of y. In order to do that, we're going to rewrite the function in the exponential form. Okay, we got the fraction. So we can rewrite y as x squared plus c to the -1. All right. So then we can use the power rule to find the derivative of this function. So y prime will be -1. So you bring down the exponent, put in front, times x squared plus c to the -2. So you subtract 1 from the exponents, you get -2. But then remember, x squared plus c is a function of x, so you have to use the chain rule to find the derivative. So you need to multiply the derivative of the function x squared plus c. If you remember before in Cat 1, and x squared, you get 2x from the derivative, and the derivative constant c, you get 0. All right, and you can rewrite the whole thing as negative 2x times x squared plus c to the negative 2. Or if you want to rewrite in the fractions, then you just put the x squared plus c squared in the denominator, like this. So that will be negative 2x times 1 over x squared plus c squared. Okay, so rewrite like this. All right. Any questions at this point? I think this is straightforward. We just use the chain rule. Okay. So if you forget the rules for differentiation, you probably need to review Cat 1 a little bit by yourself at home. So we found the first derivative of the function. Let's just plug in this derivative into the equation and see what happens. So on the left side of the equation, we got y prime plus 2xy squared. So y prime is negative 2x times 1 over x squared plus c squared. Yes.
I'm sorry, could you track back a little bit to the claim? You said the solution of the differential equation is y over 1 with x squared plus c. How did you get that?
This is just a result that we will discuss how to solve this equation. Right now, we just show you the result. Okay. We're going to solve it later in chapter 2. Right now, we just give you the result and you can check. That's indeed the solution. Okay. Does that make sense?
So you're saying that y equals 1 over x squared plus c is the solution. We're just trying to check it to make sure it's correct.
Yeah, exactly. Any other questions? Yeah, because in the first chapter, we just discussed the concepts. You know, we have not done any techniques of solving differential equations yet. That would take a lot of time and it will be the whole topic of this semester. All right, so let's come back to the differential equation, y prime plus 2xy squared. So we already got y prime equals negative 2x times 1 over x squared plus c squared. Plug into the equation. So we got that the first term, and then the second term is 2x plus y squared, and y is 1 over x squared plus c. So you square that, you can see those two terms are identical and opposite in sign, so they cancel completely. So we got 0. And that means the equation is satisfied, right? So so y equals 1 over x squared plus c is indeed a solution to the differential equation. Agree? Okay, so you can see in this solution, we do get the arbitrary constant. And you expect that because when you integrate once from the equation to solve for y, you do get a arbitrary constant. Okay. And this arbitrary constant will be determined by the initial condition of y0 equal to -1. So why don't we just use this initial condition to fix this arbitrary constant c. So y of 0 equal to -1 means when x is 0, y equal to -1. So what you do, you just plug in 0 for x in the function, and you should get -1, right? So if you put 0 in x, you get 1 over 0 squared plus c, and the whole thing is just -1. And that's easy to, solve. So you get 0 plus c, which is c in the denominator. So that means 1 over c is -1, and you can easily solve for this equation to get c equals -1. Okay. So then the solution to the initial value problem, which involves the differential equation and the initial condition is y equal to 1 over x squared minus 1. So c is -1. So the solution is 1 over x squared minus 1. And remember, you cannot divide by 0. So x squared minus 1 cannot be 0 in the solution. That means x cannot be positive or -1. Okay. Right? If you still remember, the domain of rational functions, you want to avoid the points where the denominator is 0. Okay, all the points that make sense to the function itself. Okay, so the domain of the function y equal to 1 over x squared minus 1 is all the real numbers except -1 or +1. So if you write this domain in the interval notation, that actually involves 3 intervals. From -infinity to -1, one part, not including -1. Remember, if we use parentheses, that means the end points are not included. So in the first interval, -1 is excluded. And then we have the second interval from -1 to 1. Again, -1 and 1 are excluded. And then you have another interval from 1 to infinity, with 1 excluded. So then you just combine all of those 3 intervals, union, okay, combine them. And that will be the domain of the function. As you can see, -1 or 1 are not included in this set. But all other numbers are inside this domain. All right. So, that's why, when you take out 2 points from the whole number 9, okay, it will divide the whole into 3 subregions, right? 1 on the left, 1 in the middle, 1 on the right. Okay. Any questions about this notation? So you have to be, to learn to be used to those kind of notations. Any questions? Okay. There are different, by the way, there are different notations to, describe, to represent the domain. You can use graphs, okay. You usually draw open circles to denote the point is not included in the set, okay. But you can also use interval notations and other ways to represent the same set. All right. Well, remember, this is the thing that's very important. Okay. People usually not aware of it. When you write down differential equation, that means automatically the derivative exists. But we know from Cal 1 that if the function is not continuous, then the function is not differentiable. So we have 3 different parts, okay, in the domain. On the boundary points, -1 and 1, the function is not continuous. All right. Okay. They're not in the domain of the function. It's not continuous. So they're not, differentiable. The function is not differentiable at those 2 points. So that means the differential equation is not defined on the whole domain. It's only defined in one of those one of those parts. You can only pick up one region from the three. And the problem itself will tell you which part the domain is, which part you pick up. It says y0 equal to -1, so x equal to 0 is included in this problem, is included in the domain. So the solution to the problem only includes the part in the middle from -1 to 1, where the function is continuous and differentiable. The other two parts on the left and right are not part of the solution because we have some, discontinuous parts, right? So it only includes the part from -1 to 1. So that the domain of the function or the solution actually only includes the part from -1 to 1, and not including -1 and 1 themselves at the boundary. Yes.
If the equation wasn't subject to y0 equals -1, would we include the entire domain as a solution?
No, it does not, because as I just said, the function has to be continuous to start, but it is not continuous at -1 and 1. So you cannot go over -1 and 1. They only includes the part in the middle. So the domain of the solution will be from -1 to 1. So if you draw the graph with this function, it only involves the part from -1 to 1. All right. Doesn't make sense? So this is one thing people usually don't pay attention to, but it's important. Any questions?
So we don't include the other parts of the domain because it's continuous and there's no end.
Yeah, because you have the boundary points discontinuous for the function, so you cannot go over those discontinuous points, right? Any other questions? Let's see if anybody online. No question, then we go to the next page. Okay, so one of the things, when we try to solve an initial value problem, how do we know the solution exists? That's the first question. Does the problem have a solution at all? Or if it does, is the solution unique, or you have multiple solutions? Okay, those are some fundamental questions we want to address. And the answer is, it depends. It depends. Sometimes the initial value problem does not have a solution. Sometimes when it does, it may have multiple solutions. Okay, so let's start from an example. Consider, a previous example of a differential equation we discussed before, not today. Dy over dx equals x times y to the half, subject to the initial value, initial condition y of 0 equal to 0. Okay, we did discuss this example before, and we checked, the function y equal to 1 over 16x to 4 is indeed a solution to the differential equation. So we already verified the solution to the differential equation before in last week. Okay, if we plug in y equal to 1 over 16x to the 4 into the differential equation left and right side, you will see the equation holds. Okay. And so we're not going to repeat it. So that's one solution to the differential equation. And also it satisfies the initial condition. If you plug in 0 for x, you get the y equal to 1 over 16 times 0 to the 4th, and you get the y equal to 0. So y0 equal to 0 is also met for this solution. But the equation also has another trivial solution, y equal to 0. So that's a constant function, okay? Y equal to 0 is a constant function. If we draw the graph of a constant function, you get the horizontal line. So that's a function, okay? That function is also a solution to the differential equation. If you plug in a constant function into the differential equation, you take the derivative of constant, you get 0 on the left side. On the right side, you know, x times 0 to the half, you get also 0. So the equation is satisfied. And obviously, y0 is 0 because y is always 0. So this is indeed another solution to the initial value problem. So we got the two solutions for the initial value problem. So the solution to the initial value problem is not unique. Okay. Both solutions satisfy the initial condition and the differential equation, right? So then how do we know the solution exists, and how do we know it's unique? So we have a theorem in the following page, on the following page. Any questions about this example? Okay, let's see what it says in the theorem. Okay, again, we have a lot of mathematical languages in here, but you know, if you're not comfortable with all of those, just ignore some part, you know. The mathematical languages are always regardless, okay. Let's say what it says. Let R be a rectangular region in the xy plane defined by x greater than or equal to a and less than or equal to b, and y greater than or equal to c and less than or equal to d. Okay, so we got the rectangle region on the xy plane. Okay, if you draw a rectangle on the plane, you know, the left hand side x equal to a, right side x equal to b. The lower part, y equal to c, and the upper part, y equal to d. Okay, A, B, C, D. Okay, that's a rectangular region that contains the point x0, y0 in its interior. So you just pick at any point inside this rectangle, we call it x0, y0, the coordinates of the point. Okay. So then, you know, we have the differential equation dy over dx equal to f of xy. So let's just consider this function f of xy on the right hand side of the differential equation. So if the function f and the partial derivative of f with respect to y are continuous on R, okay. So I don't know if it took Cal 3 or not. If you do, then you should know what it means by partial derivative. Okay, so f is a function of two variables, x and y. So you can take the derivative with respect to x and keep y as a constant. So that's called the partial derivative of f with respect to x. Or you can take the derivative of f with respect to y and keeping x as a constant. That's the partial derivative of f with respect to y. Okay. So, you know, for example, when you take a partial derivative of f with respect to x, you just consider y as a constant. Okay. So if f and the partial derivative of f with respect to y are continuous on this plane region. Okay, those two things are continuous on this region. Okay, good. Yeah, good functions. Then there exists some n to I0 from x minus h to x0 plus h. Okay, contained in this rectangle region. Then what is said? Okay, then it says there is a unique solution y defined on this small interval I0. That is solution to the initial value problem. Okay, so if the initial condition is given, yx0 equal to y0. All right. So what it says in here? Okay, if I translate this language into plain words, it says, if both the function f on the right-hand side of the first order differential equation and the partial derivative of f with respect to y are continuous on this plane region. They are continuous, both are continuous functions. Then, the initial value problem always has a unique solution. So how do we know we have unique solution for the first order initial value problem? You just want to make sure the function f and the partial derivative of f with respect to y are continuous. Yeah.
Can you repeat that one more time?
Okay. So how do we know this initial value problem divided with dx equal to f y of x0 equal to y0? So that's the initial value problem. So how do you know this problem has a solution, and how do you know the solution is unique? You just need to check this function f on the right side of the equation and the partial derivative of f with respect to y, both are continuous. Okay, in the region we consider. Okay, then it always has a unique solution. And it really doesn't matter what this value y0 is. Any value y0 you put for this, y at x0, it always has a unique solution. Okay, so the first order differential equation always, has a unique solution if this condition is satisfied. All right. So let's do one example and see you see what happens. Okay. So let's see the previous example. Dy with dx equal to x to y, x times y to the half. That's the differential equation, and the initial condition y of 0 equal to 0. So we got this function f, which is the right hand side of the equation. So f equals x times y to the half. And the initial condition y of 0 equal to 0 means x0 is 0 and y0 is 0. Okay. So identify those conditions first. And then we want to check whether f and the partial f, partial y, they are continuous. Okay. There is no problem for this, f itself. Okay. But when you try to find the partial derivative of f with respect to y, what happens is, you use the power rule again, right? Y to the half. So you don't have to worry about the x, just keep it as it is. When you take the partial derivative of y with respect to the partial derivative of f, with respect to y, you just keep x as constant. So you just take the derivative of y to the half. So you're going to get a half times y to the negative half using the power rule. Okay, so y to the negative half means, you can put the thing in the denominator. And you also get half. So that's 2 in the denominator. So the partial derivative of f with respect to y is actually x over 2 times y to the half. Or you rewrite y to the half of s squared root of y. Okay, so that's x over 2 squared root of y. Now you can see this partial f, partial y is not defined at this point or region, the origin. So it's not continuous there, right? So partial f, partial y is not continuous at this, initial point. Okay, f itself is continuous. Okay, x times y to the half, that is continuous. You can plug in 0 for x and y, but you cannot plug in 0 in the denominator in the partial f, partial y. So the partial derivative of f with respect to y is not continuous at the initial point. So the condition for the theorem is not satisfied, right? Both need to be continuous in order for the initial value problem has a unique solution. So that means the problem does not have a unique solution. And we do know there are 2 solutions. X to the y to the half, 1 over 16 x to the 4th and the y equal to 0. Both are solutions to the problem. If you remember the previous page, we have 2 solutions to the problem. And we have verified that the conditions in the theorem are not satisfied. Okay. So the problem does not have a unique solution. Does it make sense? Okay. That's the second section of this chapter. We're going to do section 3, start section 3 on Wednesday. So let me take the roll for the people online before you go. And you guys should sign paper roll if you are in the room, okay, before you go. Okay, let's see. Let me take the roll online and you guys just sign the roll yourself. In the class, let me just stop the recording first. Okay, I guess I need to do that first. I want to do that first.